Okay, so analysis of variance, otherwise known as ANOVA. A cosmetic manufacturer's regional distribution center has 4 workstations for packing cartons for shipment to small retailers. They collected data for the number of cartons packed per day over a recent week. They want to know if there is a difference in the mean number packaged across stations. So here's our data set, a picture of our data set. We've got the station number and then the number of cartons packed. In the right, we see here side-by-side box plots. So it does look like there is a difference in the number of cartons packed per station, right? Station 1 and 2 are shifted up from station 3 and 4 in the number of cartons that they're packing. So how do we analyze this kind of a data? Well, we have independent samples, so why don't we use a bunch of independent samples t-tests? We could compare station 1 to 2, 1 to 3, 1 to 4, etc. Well, the problem is that using the t-distribution to make more than one comparison of a pair of independent samples actually drives up the chance for at least one type 1 error. This is called the family-wise error rate. More on this later. For now, we're going to learn ANOVA. So the null hypothesis in ANOVA is going to be that the means are all equal. So mu1 equals mu2 equals da-da-da-da-da equals mu k for however many groups it is that you're comparing, however many populations it is that you're looking at. And the alternative hypothesis is that at least one of these is different. Notice we can't specify a direction of how they're different, right? That's because this null hypothesis is called a compound null hypothesis. It's multi-directional. There are many ways that it can be different. So the alternative is always going to be just that at least one is different. Now we've got to get some kind of hairy notation out of the way. We're going to let capital I denote the number of groups. In our example with the number of stations, we have 4, so there are 4 groups. Our I would be 4. Little I denotes the ith group, and little j is going to denote the jth observation. So yij, if it's y12, this denotes the second observation in the first group. N sub I is the sample size for the ith group. Y bar I is the sample mean for the ith group. N dot is the total sample size across all groups. Y bar bar is the overall sample mean combining all data across all groups. All right, so now we're going to define something called mean squares. So you've already talked about sum squares a little bit. We have a sum squared within. This is at the heart of our sample standard deviation calculation. This is the distance from an observation up or down to its own sample mean within a group. So that's why they call this the sum squared within. There's another way that you can write it over here, but we're going to pay attention to this one on the left. The degrees of freedom for this sum square, this measure of variability in the y's, is n dot minus I. So your overall sample size minus your number of treatment groups. Think about it. You're using the sample size of one treatment group to make all your comparisons within one treatment group, and if you had degrees of freedom for that, it would be n minus 1. And you have that for all your treatment groups, so you're docking it by 1 for each treatment group, so it's n dot minus I. And then a mean square is something new that we're going to define. A mean square is a sum squared divided by its degrees of freedom. So the sum squared within divided by the degrees of freedom within are the mean squared within. Now why are we calling it within? Because this comparison is looking at the distance of an observation up or down to its sample mean within a group. The sum squared between is going to look at the sample mean of a group relative to the overall grand mean. So how many comparisons are we making here? We're looking at the sample mean for the first group minus the overall grand mean, the sample mean from the second group to the overall grand mean, third group to the overall grand mean, fourth group to the overall grand mean for our example. So the degrees of freedom for this one is going to be the number of groups minus 1. So again, you can still think of the degrees of freedom the same way we always have, as being docked by 1. All right, and then of course the mean squared between is the sum squared between divided by its degrees of freedom. And last but not least, we have a sum squared total. So this is another measure of variability. This one is also analogous to the sample standard deviation that you learned in the beginning of the semester, but it's looking at the distance of an observation up or down to the overall mean. So of course, we're doing n dot comparisons there, and we're docking it by 1. So that's our degrees of freedom. And of course, the mean squared total is the sum squared total divided by the degrees of freedom total. So remember that a mean square is a sum squared divided by its degrees of freedom. All right, so consider the deviation from an observation to the overall mean written in the following way. Do you agree that yij minus y bar bar is yij minus y bar bar minus y bar I plus y bar I? Of course. All we did on the right side was we added and subtracted the y bar I. But notice what we've done in writing it this way. This is that part of variability that we did in the sum squares that we called the total variability, the distance from an individual observation all the way to the grand sample mean. This one was our within group variation. It looked at the distance of an observation up or down to its own sample mean. And this was the between group variation from that between group sum of squares from a sample mean of a group to the overall grand mean. So the within variation plus the between adds up to the total. And it actually works out that when you sum over all of the observations and all of the groups and square each of these deviations, it works out that the sum squared within plus the sum squared between actually equals the sum squared total. So this breakdown of the variability in the y's according to these different components is at the heart of how we do the ANOVA. It's a comparison about means, but we're going to look at the variability to say something about our means. How we're going to do that is we're going to look at the ratio of the mean squared for between, so how much variability is accounted for by the groups themselves relative to the mean squared within. That is, how much variability is just natural error variation within a group. If the distance, so let's take a look at the scatter plot that we started with. So if the distance between these groups, so let's look at 3 and 4. We can see that there is a little shift in the medians, so there's probably a shift in the means too, okay? But it's overwhelmed by how much variability there is in each group. We would probably say that's not a significant difference. But then look at station 2 to 3. It looks like there that there's a significant shift that might be a little bit larger than the natural variation within each group. That's the same game that we're playing. That's the same game that we're playing here. We're comparing the variability that's accounted for by the groups themselves to the natural variability that happens within a group. And that thing is going to have an F statistic. All right, so if the data indicates large differences in group means compared to each other relative to the variability within groups around group means, Fs will be large. Big values of F indicate evidence against the null hypothesis. If the group means are the same, the variability between them should not be larger than the natural variation of the data within each group. So the F distribution has degrees of freedom for the numerator, between, and the denominator, within. We say that F is distributed as an F with nu1 and nu2 degrees of freedom. The picture on the right is from Wikipedia, and it illustrates a couple F PDFs. The p-values for the F test in the ANOVA are the tail area quantities that will be calculated for you using R. We've got 4 assumptions that need to be met in order for the ANOVA test to be valid. The errors have to be independent, normally distributed, mean 0, and have constant variance across all treatment levels. What are the errors? It's the deviation of the observations around the sample mean. Okay, well, the errors are around the population mean, but we have a sample that we're going to be looking at. We'll look at the residuals. Okay, So we have to fit the model to check the assumptions since we need these residuals. So here's the R code that we're going to use. Notice that I defined an object in R called fit. And whenever I fit a model, I'm almost always going to call it fit. And then I use my definition character here, my less than dash sign, and I use the function AOV in R for ANOVA. I attached my data set, so I put my response variable, my quantitative response, my Y, my number of cartons, on the left, and then I use the tilde sign and put any predictors that I have. Right now we're only doing a one-way ANOVA, so I have one predictor. Now notice that I put the factor function around station. Why did I do that? If you remember, the list of stations in my data set was not words, it was numbers. It was denoted as station 1, and then 2, and then 3, and then 4. And so R thinks that's a quantitative variable, but for the ANOVA function to work correctly, we need for R to treat it like a categorical variable. And so we'll do that by calling it a factor inside R. And then to get the output for the ANOVA table, we just use summary of fit. So that's how you get your ANOVA table to be output from R. And it looks just like what's on your screen. Notice that we've got a row for our predictor variable and a row for residuals. Those are the sample estimates of the errors. All right, so notice in the ANOVA table that it gives us our degrees of freedom, okay? The top line in any ANOVA table is always the between groups stuff that we were looking at, and the bottom line is going to be the within group, because residuals means errors, means within. It does this because when it computes the F, remember that's the ratio of the mean square between divided by the mean squared within, so it just takes this mean square divided by the mean squared within. 493.1 divided by 119.6 is 4.122. So if I erased one of those mean squares on an exam, you could figure out what it is. Or if I erase the F value, you could figure out what it is. You could also figure out the degrees of freedom. How do I know the degrees of freedom for between? For my groups is 3 here. Remember that was the number of groups minus 1, and we had 4 groups, so the degrees of freedom are 3. How could I figure out the degrees of freedom total? Well, the degrees of freedom between plus the degrees of freedom within equal the degrees of freedom total. So the degrees of freedom total are going to be 19, which is n dot minus 1. Okay, and then of course, the degrees of freedom within is your n dot minus your number of treatment groups, so 20 minus 4 is 16. And how could I get this mean square if it was erased? Remember, that's a sum squared divided by its degrees of freedom. So this 493.1 is 1479, which is the sum squared for between, divided by 3, which is the degrees of freedom for between. Okay, so that's how the numbers in the ANOVA table come together and how you could figure them out if some were missing. So let's check our assumptions now. So we've got our first plot, which is new. It's called a residuals versus predicted plot. And what we're going to do is imagine a horizontal line at 0, and the residuals are here on the y-axis, and the fitted values are here on the x-axis. And so what this is how far above or below the mean our observations are. Now on a one-way ANOVA, which is all we've learned so far, we'll talk about what that means later. But when we only have one predictor, that's a one-way ANOVA, it's going to turn out that these residuals are going to have mean 0. But what we're going to practice looking at this because we're going to need to get good at it with regression and two-way ANOVA. What this means is if I looked at each group and I averaged these positive residuals with these negative ones, would they cancel each other out to have a mean 0? So it does look like everything balances out above and below my 0 line. So I'm going to say that there's little to no evidence against the errors having mean 0. So little to no evidence against errors having mean 0. And the other assumption that I can check on this plot is that the errors have the same variance no matter what group you're in. So are they just as spread out no matter which group you're in? For the most part, yes. I don't see any gross violations of this. So I'd also say little to no evidence against a constant error variance. Now, I should have pointed out that we also ran a hypothesis test to check whether there was a constant error variance. In this Bartlett's test, this p-value is testing the null hypothesis that the variance is the same across all the groups, and the alternative that it's not the same, that there's a violation. We have a very high p-value, so we're going to fail to reject the null. Little to no evidence against the constant error variance, against the error variance being the same no matter what group you're in. Okay, and then we need to look at this QQ plot to determine whether the errors have a normal distribution. Now, this plots the theoretical quantiles against the sample quantiles. So it plots where the points should be if they were from a normal distribution against where they actually are in their distribution. So if these observations were from a normal distribution, this plot would be linear. Anytime it makes a shape, like a U shape or an upside down U shape or an S shape or an inverted S shape, we're going to question whether these observations came from a normal distribution. So here, I see a little tiny hint of maybe an S shape starting, but it's not really that bad. So I'm going to say that there's little evidence against the errors having a normal distribution. It's not a glaring shape being made. Little evidence against the errors having a normal distribution. Okay, so we've checked our assumptions except for the errors being independent. We're going to talk about how to check that more when we get to time series. For now, we're just going to assume that the errors are independent, that there's nothing making a dependence in those errors. And we're going to say that our assumptions are met. And now we can look at the ANOVA output to do the actual ANOVA test. All right, so we've got our p-value here for our ANOVA test. It's 0.02. So if our alpha level is 0.05, our null hypothesis for the ANOVA is that the mean number of cartons packed for station 1 equals that for station 2, equals that for station 3, and equals that for station 4. And the alternative is that at least one is different. We've got our F statistic, which is 4.122. That's our test statistic. We've got our p-value, which is 0.0241. And we can compare our p-value to our alpha. And the p is low, so the null must go. And step 6 is making our conclusion. So there is significant evidence at the alpha equals 0.05 level to conclude the mean number of cartons packed is different for at least one of these stations. Okay, so we've got an ANOVA test that rejects, and it tells us that there's a difference somewhere. We can guess where by looking at our side-by-side box plots, but we don't want to guess. We need to know. So what do we do about this? There are differences somewhere, but where and what exactly are the differences? This is the question of the topic of multiple comparisons. There are lots of methods to choose from. The one that we're going to use this semester is Tukey's. Tukey's controls the family-wise error rate for all pairs of t-tests. There is a modified Tukey for when the sample sizes are different that does so approximately. Chaffee is another popular method, but we're not going to use it. It has the least power, that is statistical power. It's the most conservative for all comparisons, but you can test anything you want using it and as much as you want, and it always controls the error rate. Dunnett's is a popular method. It compares each category to a control category. And then Sue's best multiple comparison to the best compares to the best, which can be defined as the highest or lowest mean. Okay, so we're going to focus on Tukey's. And you just run that by typing in this code, Tukey HSD, of whatever you called your fitted model. And remember, I almost always call mine fit. All right, so it spits out this output for us. And it tells us that it's giving the pairwise comparisons for our station variable. So let's look at how to read this. 2 minus 1 means it's comparing station 2 to station 1. And it's saying that the difference in the sample means for station 2 and station 1 is 4.4. It's giving us a confidence interval for that difference, and it's giving us a p-value for that difference. So we can see that this difference is not significant. Our p-value is very high, and we also can gather that from our confidence interval because it contains 0. It's an interval for the difference in means, and it contains 0. So 0 is a plausible value for that difference. So we've got the comparisons for all 6 pairwise comparisons, 1 to 2, 1 to 3, 1 to 4, 2 to 3, 2 to 4, and 3 to 4. So these are simultaneous 95% confidence intervals that we're getting here. All right, so consider comparing 4 to 2. Which one has the larger mean? So that's this comparison right here. Well, the average number of cartons packed for station 4 minus the average number of cartons packed for station 2 is negative 20.4. So what does that mean? That means that station 2 has the larger mean number packed. This difference is significant because the p-value is 0.04. So 2 is significantly larger than 4. The average number of cartons packed is significantly larger for station 2 than it is for 4. And there are not any significant differences elsewhere. All the other p-values are above 0.05 for all the other comparisons. We can also make a plot of Tukey's output. Sometimes this is handy just so you can scan. You can see here that all of the confidence intervals contain 0, meaning the p-values are going to be high, not significant, because 0 is a possible value for that difference, except for the station 4 to 2 comparison. So it just mirrors what we just saw in our numerical output.